So last time we introduced classes, and we saw that classes are a way to create objects. And I'm dripping from the rain and getting this thing all wet. And we saw that classes are a way to create objects, and then objects are actually what we want to. I made it so much worse. Are what we want to actually work with. So let's dive into that a little more and talk about how objects are represented in memory, and when we use our classes to create new objects, what's going on with that. And we're going to find that the stack isn't going to be enough to explain how this all works. We're going to have to talk about heap memory. So let's start talking about that today. And I know Monday's lecture, there's quite a bit coming at you at that lecture. There's a lot. When you first learn classes, it can be overwhelming. So as we're talking about heap memory, I do want to reinforce classes and objects, the differences between those, this idea of state and behavior. So hopefully we'll solidify that content as we're talking about the heap. So lecture task 2 for this is today's lecture task. And for this, we're going to have to think about the heap and references. References, the one word I introduced on Monday that we really didn't talk about yet. We're talking about that all day today, all day Friday. References. So for this, create a class named Sale that has a that's static. Is that just the rain? Sale that has a constructor that takes one parameter that's a double, which is named exactly %off with a capital O. When we're doing testing, remember that you can only, in your test, access classes, variables, objects, etc., that have been explicitly named in the question, because I'm going to have code on Autolab that your tests are going to run against. Your tests are going to run against my correct and several incorrect solutions. So if you're testing a variable that you've named, those tests are they're gonna error out, and you're gonna see that kind of sideways face in Autolab and says error running your tests on correct solution and all the incorrect solutions. In this case, %off is a named variable. We know that that's going to be a state variable of the Sale class, so you can and should access that in your testing. So whenever I name a variable like this, that should be your kind of warning sign or alarm should go off and say, hey, that's something I'm going to want to access in my test suite. If I don't name it, that's something you're not accessing in your test suite. So %off as a variable, highlighting var to make sure you remember in that constructor, use var there. This is something that can change. And in my testing, I'm going to change %off. I'm going to say, whatever sale object I created, dot %off equals, and then some value. So that can change. It is a var. And then a method named update price, which takes a double and returns that double with the sale applied. Let me back up a little bit. Update price is going to take the price of an item and then apply the sale to it. So if we have a %off of 20, that would be a sale of 20%. So if I get update price called on 100, I need to return 80 because I'm going to take that price and update it with the sale applied. So if I get update price of 100 and %off is currently 20, I'm going to apply that sale, do a little bit of arithmetic, and return 80 as the return value of that. So these sale objects are going to be able to apply their %off to a price that they're given through the update price method. Create another class called sale testing item. This is specifically just for testing this lecture task. We will eventually add this functionality to the item class, but for just testing this functionality, since we don't know inheritance, polymorphism yet, which we're going to use in the item class itself, we're going to create a separate class just for testing this thing. So we call it sale testing item. It's an item that's used to test sales. So the sale testing item is going to have the similar structure as an item. It's going to have a constructor that takes a string and a double, the description and price. But it's also going to have two extra methods, add sale. Oh, and notice, like this constructor, for example, I didn't say what to name these variables. You probably end up naming them description and price. That'd be the most sensible thing to name them. But since they're not, that's not defined in this question, those aren't defined names, you can't access them directly in your testing. So that's the difference between I named this variable, we're all going to have that same name. I didn't name these variables, so you can't access those. We're all going to have different names. And in my auto lab, I'm going to name them something really silly just to drive that point home, that you're not going to be able to just guess what they're named. So these ones are not named. We cannot access them in our testing. And then these two methods, add sale and price. Add sale is going to take a reference to a sale object and add that sale to this item. So if I have 3 different sales on this item, maybe it's just straight up on sale. Maybe there's another sale that's applied when you swipe your Shoppers Club card, and another sale that's applied because somebody had a coupon. So maybe there's 3 different sales on a single item that need to be applied. We're going to call add sale to add all of those sales to the item, and then have all of those percentages apply multiplicatively. So if it's 10% off and another 10% off on a $100 item, that item would be $81 in the end. You would apply the first sale, get to a price of $90, and then on that price of $90, apply the second sale, which would be $9 off to get to $81. So multiplicatively, in the document, I explain that a little more just to make sure we're all on the same page with that. And you should store these in a data structure. There's a variable in here. We're starting to get to the point where you have to design a bit of your solutions. Implicitly in here, you're going to have some state variable in sale testing item that stores a data structure of sales. I don't ever say you have to create a data structure of sales, but implicitly you have to do that to get this done. So in your sale testing item class, you want probably a list. I guess I am just explicitly saying it now, but I won't always, just because it's the first one I am. A list of sales, and then when add sale is called, you want to append or prepend that new sale, reference to a sale, to that list. And then finally, when price is called, take the price from the constructor, which this price should never change. Take that price from the constructor for each sale that was added with add sale, call update price, and then return the final price with all of the sales applied to it. So we're getting into a situation where there's a few moving pieces here. Questions are getting a little more complex, and this is where we need to be at this point. So creating a few classes, having those classes interact with each other, and having, especially right here, something passed by reference. Let's take a look at this and see how we're going to do this stuff. I don't know if anyone else can hear. It's bugging me that it sounds like there's a little static. Do you want to get close to my laptop? All right, so when we talked about the stack, the only values that go directly on the stack are what we kind of call primitive. They're called primitives in Java, so they compile to Java bytecode as primitives. So I still use that term. But these values, doubles, floats, ints, longs, shorts, chars, bytes, and booleans, and also references to objects will go on the stack. And that's it. Nothing else goes on the stack. And I'm sure you can think of quite a few things that you have in your programs that are stored in memory that are not on this list. Lists themselves, for example. A list of ints isn't in this list. Strings, not on this list. The player class we created last time, not on this list. So where are these things stored if they're not stored on the stack? Of course, the big title slide at the beginning should tell you that's going on the heap memory, but let's talk about what that is. Oh, and it's on this slide. It's going on the heap. So let's talk about what heap memory is, where all of our other objects are going besides this very short list of values. So let's talk about memory heap. So first, let's try to ignore that there's something called the heap that exists. And let's try to run this example, which contains a list which is not one of those types from the previous slide. And let's try to run this example and trace through it using only a stack. And let's see how we do. Let's see how we fare when we do that. So we're just creating a list with 2 values, creating a few more values, and then prepending 1 to this list. Let's take a look at how this would work on the stack. I had these crossed out because this is not, I don't want somebody studying this slide and saying, oh yeah, lists go on the stack. They don't go on the stack. But if they did, how are we going to do this? So we're going to get to the list, we're going to go to the stack, and we have two values we have to add to the list. We have two ints, so we need to allocate 64 bytes of memory. We got to get, or 64 bits of memory, and get those 64 bits on the stack somewhere. A fixed amount of storage space. We're going to allocate space for that and store these values 2 and 3 on the stack in memory. Then we have a few more variables, values in this case, that we want to add to the stack, x and y. And the way the stack works, we're going to find the next available space in memory on the stack. We're going to go to the bottom of the stack visually, or the top of the stack, kind of using stack terminology. And but the next available space in memory on the stack, we're going to add those values, 5 and 12 in variables x and y. And then we get to a big problem here. We want to prepend 1 to the list. How are we going to do this? Knowing that we have no space, like we don't have any gaps in our stack, we have no space right here, we would want to add 1. So how do we do this? So let's take a look at our options. We have a few options that we might be able to do. Well, why don't we expand this current list, make it bigger, and then just add space for this value 3. Then we have this big problem where the space that we want to add is either going to conflict with command line args if we add 1, or we move 2 and 3 down and make space for 1. But now the value 3 is going to conflict with the variable x. We already allocated that space for another value. We can't just say, oh, this space is for the list now, because x needs a home. It needs to go somewhere. So we can copy x down to here, copy y down to here, and just move everything down by 1. So if we want to add a value to the list, we're just going to move everything below the list down by enough space, the amount of space that we need, and then expand the list. This is bad for a few reasons. One, it's just too slow. If every time you're modifying a list, you're moving around the entire stack, maybe the list was the very first thing added to the stack, like it is in this case, and then we add like hundreds of more variables, maybe even more lists. Maybe we have a gigabyte of data in a data structure that we're storing after that, assuming everything's on the stack. We'd have to move that whole gigabyte of data down every time we want to add like one more byte to this list. That's not something we're going to do. Way too slow, way too inefficient. And it also violates LIFO, our last in, first out data concept of a stack. We're not using this as a stack anymore. We're modifying values right in the middle of the stack. That violates LIFO, and one of the reasons we don't want to violate LIFO is because LIFO is really fast. It's very slow to modify things in the middle because we have to move everything around, shuffle everything around. It's just not something we want to do. All right, option 2. Well, let's just take that list and add it to the end of the stack. We have all kinds of room at the end of the stack. So let's add it there, and then just leave a gap in the stack. So this is still too slow because, again, what if that list is a gigabyte of memory that we're going to pick up from the middle of the stack, put it at the end, and then add that one value to it. And then we also have a huge gap in the stack. What do we do once we're popping values off the stack? What happens when we get here and we just see a big empty space? I guess we would just cut that out, but we got to rewrite our JVM to be able to handle situations like that. And also, we still violated LIFO. This isn't a last in, first out data structure anymore. We're just randomly moving values around all over this list, all over this stack. It's no longer a LIFO data structure. All right, so let's get to the actual one. Let's get to the one that we're going to use. Let's get to the one that our computers are actually using when we run our programs. The memory heap. We're having trouble doing this with just a stack, so let's introduce memory heap, or heap memory, or heap space. I'll use those terms interchangeably. If the word heap is in there, we're talking about this, heap memory. Instead of storing that list on the stack, we're going to store it in a separate portion of our RAM, completely independent of the stack. So when we start our program, we get stack memory, that we can use for our stack purposes, and then we can also ask for heap space or heap memory more dynamically. We can say, hey, I need enough space to store a list with 2 elements, and then somewhere in memory, we get that list, we can store that list, and then what we put on the stack, what goes in the variable list, is only going to be the location in RAM where that list can be found, not the list itself. So all we're going to store is like the instructions or the roadmap or something to be able to tell the JVM, hey, this is where you can find the list. It does not store the list itself, it stores the location of where the list can be found, which is what we call a reference. So we're storing a reference to the list, not the list itself. The list itself is living somewhere else in some other memory that's not the stack. And then in the variable, we're just going to say, where can we find, in the case of lists, where can we find the first element of the list? And then that first element is going to tell us where to find the next element, and so on, until the end of the list. Now when we get to our situation where we have to prepend 1 to the list, we're not modifying our stack. We're not modifying the structure of our stack at all. We're just going to heap space, asking for more heap space, getting that value 1 added to heap space or heap memory, and then updating the value of the variable list to a new reference, to a reference to this value 1, which has a reference to 2, which has a reference to 3, and then storing that in list. So list is always only storing 1 reference, so it's always going to be the same amount of memory that we need to store that reference. It's always just a reference, but that reference can change. Since list is a var here, list stores a reference, and it's a var, so we can change which reference is stored in list, which we do here. So we're going to store a different reference to this 1 instead of the 2 to change the list. Didn't have to modify the structure of the stack, we just modified one of the values that a variable stores on the stack. Same amount of memory usage. We asked for more memory over here. So the heap gives us much more flexibility. This is more dynamic memory, where the stack is more static, it's rigid, it's very structured. Heap is very dynamic. You can ask for heap space whenever you want. Whenever we say new, whenever we use the keyword new in our programs, we're asking the OS or the JVM for more heap space. Give me some heap space. I need enough space to store this player object or whatever we're creating. I need enough space to store whatever object I'm creating. Give me that space somewhere in RAM. I don't care where it is. I don't know where it is. I don't know and I don't care. The JVM or your operating system can even move heap space around. I don't even care if my objects are moving around in heap space. I don't care. I just don't care. As long as we get a reference to the location where that object is stored. So no matter where that object is stored, give me a reference, which are the directions of where to go on the RAM stick to find my data. I don't care where it is, just give me a reference to it. And this is the only thing that's stored in our variables, aside from our doubles, ints, chars, booleans, etc. Aside from those, everything else, every other variable and value, only stores a reference, which is where that object can be found in heap memory. That's why when talking about the stack, we stick with ints and doubles. I think I only did ints and doubles in lecture, because most everything else is stored on the heap. So, and this includes everything. Oh, I just said that. But everything else, including your lists, maps, arrays, any strings, any built-in class that we've used outside from the ones listed on that one slide, any classes that you create, the item class from lecture task 1, the sale class, the sale testing item from lecture task 2 that we have today, all objects of those types are stored in the heap, and the variables only store references to them. And whenever a method is called that takes an object that's stored using a reference and is stored on the heap, this is going to be what we call pass by reference. So only the reference is sent to the stack frame, to the method that's being called. If you want to get technical, it's technically passing a value. It is passed by value, but the value is a reference. So if you want to get technical with that one, the value that's being passed is a reference, which is slightly different than pass by reference, but at this level, we can gloss over that a little bit. In 220, you'll have to care about the difference between those two. So let's take a look at a slightly modified example from last time. Last time we created 2 players and stored them in player 1, player 2. Let's do something a little bit different here and say new player at 0, 0 with max HP of 10. Create a new player. What this is going to do is ask for heap space, enough to store these six was it? The 6 state variables for the player class, enough memory to store all 6 of those variables, and initialize, through our constructor, initialize the X and Y location and the max hit points. And then what new is going to do is return a reference to the player that's created. So we got space for those 6 values. We populated those 6 values, running our constructor and our initialization code. And then new returns a reference to that object that was created on the heap. So this returns a reference. And then player 1 only stores that reference. So player 1 isn't actually storing a player at all. It's storing a reference, which is, how do I find this player in memory? Where is this player object? So when we do something like player 2 equals player 1, this assignment, my computer does not want to highlight that line. This assignment is going to be by reference. So when player 2 equals player 1 is executed, player 1 only stores a reference. Player 2 is going to be assigned that value of that reference, not the object itself. The object is not being copied. We're not getting a copy of player 1. We're getting a reference to the place in memory where this player was created. Only one player has been created in this program. Only one. And then player 1 and player 2 both refer to that single object on the heap, that single player object. So when we do something like player2.move, we're accessing the behavior of player 2. Whenever we see the dot operator, we're accessing state and behavior. And more specifically, now that we're talking about heap, what we're doing is following the reference. Player 2 dot, that says player 2, you're a reference. I really don't care about the reference. I don't care about the reference at all. But once we hit the dot, that's saying whatever you refer to, whatever object you're currently referring to, go to that place in memory, go to that place of the heap, and access that object, and then do something with that object. So when we say player2.move, we're saying player 2, the reference, access your object and access this behavior, call the behavior of move with inputs 3 and 4, with arguments 3 and 4. And from last time, we know that's going to move this player from 0, 0 to the position 3, 4. And since this dot accessed that place in memory, and player 1 and player 2 refer to the same object, guess what? Player 1 and player 2, they refer to the same player, they both move to 3, 4. So if we're checking the location, both of these will pass. This will be a passing unit test. Both players move to 3, 4. And I say both loosely. Both variables move to player to 3, 4 because they're both referring to the same object. There's only one player in this code. They both refer to that same player. And of course, I'm going to throw, when we get to the LO2 quiz, I'm going to throw this stuff at you. When you're looking at the quizzes, look at how many times the keyword new appears. That's how many objects are on the heap, in general anyway. Things like lists aren't going to be, won't use the keyword new, but they do still create new objects. But whenever it's a class that we created, new is going to create a new object. If you only see the keyword new once, you only have one of that type of object. So when I have like player 1, player 2, player 3, player 4 on a quiz, and new only shows up once, you know they're all referring to the same one. So any change in state and behavior, or any change in state is going to be seen in both of those variables. And we also saw something, we're seeing side effects again. We have move, which returns unit. And you notice that we see the result of move after that method call is over. This method call both returns unit, and after that method call, well, this is true for every method call, but after the method call ends, the stack frame for that method call is completely destroyed. So if the stack frame's destroyed, there's no memory of this method ever being called, and it returns unit. Why did we call that method? What the hell could change? Nothing on the stack can change. Nothing on the stack at all can change after that method call returned unit and the stack frame's gone. No matter what it did, it can't change the stack. But what it can do is follow the reference, in this case of player 2, follow that reference to the heap, make a change in heap memory, and then that change in heap memory will persist after the stack frame is destroyed, because the heap is not going to be destroyed along with that stack frame. So we do actually see this change. We have this side effect from this method call. We see that change in player 1 and player 2 after the stack frame is destroyed and returned unit. So whenever we see new, we're creating a new object. There are some cases, and that's the only way a new object is created, is through the keyword new. With list, map, etc., we don't use the keyword new, but when we say like list of 1, 2, 3, internally it is actually calling the keyword new. If you follow into the Scala library, into the standard library, you will see that when you call that method, it is actually calling new list at one point in that code. We just don't do it directly, but the code that we're calling does use the new keyword. All right, let's see an example, and let's get some more visuals here to try to solidify what's going on here. So here's another language-independent example. It's not meant to be any specific language. Again, it might accidentally be a language. It might accidentally work in a certain language, but it's not meant to. It's meant to be just no specific language at all, just so we can focus on the concepts. So for this, I have a class named class with state with one state variable, which will be initialized to 0 when an object of this type is created. I'm going to have a main method that creates an object of this type, calls this method add to, or function in this case, function add to state, which is going to take a reference to a class with state, the way we're calling it. It could take anything, though, with a state var, and add one to its state variable. And then we're going to print that state variable to the screen, which should, of course, print 1. So that add to state function call has the side effect of modifying this object on the heap, and data.state var at the print line is going to be 1, even though it was initialized to 0, and all we did was call a function that doesn't return anything, and its stack frame is destroyed. We're still going to see a side effect that was created by that function call. So let's visualize this thing. Let's step through this and see not only what's going on in the stack, that RAM should say stack, that's going to be our stack, and see what's going on. So the very first thing we do, we start with our main program, our main function, and the first thing we do is create a new instance of class with state, a new object of type class with state. So we're going to ask the operating system for some RAM in heap space, which could be anywhere on the machine. Again, we don't care. We don't know or care where exactly this is. We just know it's somewhere that's not in our stack, and it's not being used by another program. So we're going to ask for some memory. We're going to say we need memory enough for an object that stores 1 int. So it's going to be 1 int's worth of memory plus whatever overhead my class has for that object type. So we get this memory. We're going to initialize it. We get memory for state var. We're going to initialize it to 0 because that's what our code tells us to do. And then we're going to have a reference, this at 387. The number's not critical here. I just made up a number for this. But we're going to get some number that says that's going to be used as the instructions of where to find that in heap space. The numbers aren't going to be meaningful to us, but they're going to be meaningful to the program. They're going to be meaningful to Scala. And then that's what we store on the stack. So when we create this variable named data and put that on the stack, what we store in the value of data is that location in memory. And I should point out, the JVM does obfuscate that quite a bit, where we can't actually directly find out where it is in memory. Again, we don't know, we don't care. But we do get some value that says this is where you can find it. It's going to look like some at when we run the debugger. We're going to see that it's some at and then some randomish number to us. I'm sure it's very meaningful to the machine. It's not meaningful to us. What's meaningful to us is matching these. At 387 means this object that's at 387 in that location in memory. So we can match those. And if we have two variables that both store at 387, we know they're referring to the same object. That's what's important to us. So that reference, where can this be found in memory in heap space? That's what's stored in the variable. Now when we call our add to state function, we're going to pass the value of data by reference, or pass the value, which is a reference, to the parameter input, create the stack frame. In the stack frame, we have the parameter assigned to the argument. So input has the value at 387. It refers to the same object that data refers to, which is this object on the heap. And then inside that function, when we say input.stateVar plus equals 1, we're going to go to input. We're going to look up this. Okay, what's this input? Input is at 387. Okay, that's a reference. Got it. Dot. Dot means from input, take your reference and follow that reference over to the heap. So the dot means head over to the heap, follow your reference and head over to the heap where that object is. And then what are we doing when we get there? We're accessing state var. So go to state var and increment it by 1. So we actually went over to heap space and made a change to this object when this function is called. So even though this function doesn't return anything, we did change the state of this object and therefore change the state of the program. The program is in a different state now after this function call. Even though that stack frame is gone, input is gone, but in the meantime, we took input, followed its reference to heap space, and made a change. That change persists after the function call returns. And now when we say data.stateVar, data dot follow your reference, find stateVar, guess what? That's 1 now, not 0. Because when that function was called, it passed the reference of that object, and then the function followed that reference to heap space, made a change. We can see that change after that function call ends. And the program ends. All of our heap space and stack space is freed up, given back to the operating system, and everyone goes about. All right, so let's go head over to IntelliJ. I want to do the same example, but I want to run this in the debugger and show you what it's going to look like when you run in the debugger. So for your LO2 quiz, it's going to be the same structure as the LO1 quiz. You're going to get, which not all of you have even taken yet, but you're going to get code samples, and you're going to have to trace through the code samples, but this time you'll have to be focusing on the heap as well as the stack, and tell me all about both of these types of memory. To study for that, it's really helpful to go through the debugger and take any code sample, any example code that I show in lecture that you write yourself or you write for your projects, and run them in the debugger and see how stack and heap are being affected. So let's run this in the debugger. And I want to show you that we're going to see the same information that we just saw in the slides, that we just visualized in the slides. So I'm going to run this in the debugger. Very first thing we're going to do is create this class with state. And of course, we're not language agnostic anymore. We're of course in Scala right now. We're going to move into this class with state. We're going to call the constructor. We just have one state variable. Oh, I named it state instead of state var in this example. But we're going to create a variable named state of type int and initialize that to 0, which is what we got in our constructor. So we can see 2 frames on the stack frame for the constructor call and the stack frame for the main method. And then new, once the constructor ends, is going to return a reference to class with state, a reference to the object that was created, and store that in data. So data, after this line runs, is going to store a reference to an object of type class with state. And we're going to see this at and then some number. At 800. The 800 is meaningless to us. It's just some number. But that tells us that this is on the heap. Whenever you see those at symbols, you know that this is an object on the heap. You can see that the args, the string array, that's on the heap. And this, which is the object that we're currently in, this pass by reference object, that's also on the heap. Every object goes on the heap, everything except ints, doubles, floats, longs, booleans, chars. I think that's all of them. Go on the heap. So all this stuff is on the heap. And we can expand this in the debugger and see all of the state variables, which currently state equal to 0, and that's it. Once we go into our add to state method call, we're going to pass input to it, and we can see input, it's still at 800. If I created a second class with state, I would get a different number here after the at. It would be a reference to a different object. This is the class with state that's at 800. That's where this thing can be found, is at 800. Again, it's obfuscated a bit. The 800 doesn't really mean much to the machine either, but it's a way that we can tell if 2 variables have references to the same object. And we see state is 1, but we're about to increment that. And I didn't want it to go that far. Rerun that. I want to pause inside that method call. So I have input add 800, state of 0. And if I go back to my main stack frame, I can see that data also a reference to that same object add 800. So they have references to the same object, just like we saw in the slides. And then once that's incremented, this data add 800, state is now going to be 1. Even though I never said data.state increment, data.state equals 1, I didn't change anything with data. But since this was given a reference to that object, and I did say input.state increase, I got data.state increased also. This is the same object. And we print to the screen, and we're done. So if I change this a little bit, actually let me go to the player class. Let me go to the player example we saw earlier. So here we're creating a new player, 0010. Oh, and we changed this last time and added a name. So obviously the name isn't in the slides because that's what we changed at the end of lecture last time. We're going to create that player, call the constructor, create a player, and inside this we have this, which is a reference to the calling object. For the constructor, it's the object that's being created. So we're seeing already that we're creating a player at 1828. That's where it's going to live in heap space. We're going to populate its variables according to the constructor, and we're going to pass through again and modify the state, declare any other state variables that we have in our initialization code outside of all the methods. So HP equals this. This is a reference to the player. This dot max hit points, which is 10, which was just initialized through the constructor. So HP, 10, and then damage dealt equals 4. So we initialize all those values, and then we get a reference to that player in player 1, which has all of that information that's at 1828 and all of the information that we need. Now we say player 2 equals player 1. They're going to have the same reference. They refer to the same object. So player 2 and player 1 are going to have all of the same values. And once we jump over these checks. And then once we do player 2.move, we're going into the move method, which has a reference to the calling object through the keyword this. So this is going to be that player 1828. So we called, scroll through all the, it was right here. So player 2.move, we called this through player 2, which is the reference at 1828. So this is going to be player at 1828. We get a reference to the calling object in this. So this dot x location, y location, we're going to increment them by dx and dy, and that's going to change that value. So once we call this line, so this line has executed, this line has not, we can see x location is updated, y location is not, in this object at 1828. And if we go over to our other stack frame, we're going to see player 2, this at 1828, the x location has updated to 3, and also player 1, the x location is updated to 3. They're all referring to this inside the method call on the active stack frame. Player 1 and player 2 in the main stack frame. It's not the main stack frame because we're in unit testing. We're in Scala test land. But this, a non-fun new test player. In this stack frame, player 1 and player 2 have both updated as well because they all three of those things refer to the same object. There's only one object here. New was only called once. We only use new once. We only have one player. And when we run the next line, the y location of all of them is going to update to 4. And then our check player, we're going to call it, I just want to skip over those anyway. All these tests are going to pass. We get a reference to the player, expected x, expected y, 3 and 4. We're going to call the doubles and make sure everything's working the way we want it to work. All right, I want to show one more time. Yeah, one more quick thing. Let's go back to our very first player example. Run this in the debugger. We're going to create a player, new player 0010. I'm going to skip right over that because we've seen that several times, and store that in player 1. So player 1 stores a player that happened to be created at 1829 this time. We got a different number. Again, we don't care what the number is. We just care what it is in relation to the other numbers. And we're going to do the same thing with player 2. Create a player at 7, -4 with 10 HP. I'm going to skip over that again. We're not going to go into the constructor call. But now, since I used new for both of these are now going to refer to different players because I created two different player objects. I created a player object, stored it in player 1, created a player object, stored it in player 2. So now I do have two different objects at 1829, at 1831, two different player objects. These player 1 and player 2 refer to different players, and then we get the functionality, closer to what we're used to. Check their locations. And then player2.move, this is going to be reference 1831, which is our player2 over here, because it was called with player2. So this is a reference to the calling object, which is the object referred to by the variable player2 in this case. Player2 updates, player1 stays still. Player1 still at 0, 0. Player2 at something, we can see our rounding, our truncation errors there. Then we can check them separately, attack separately, etc. Yeah, what happened to 1830? What did happen to 1830? All right, with that, that's all I got. See everyone Friday.